and start our second lesson this week, finding the cause. We're going to figure out, based on the trends that we see, what could be the potential cause. So many factors, how can we determine why the global average temperature has risen so fast? You've learned that global temperature is rising, and rising faster than during the Paleocene-Eocene thermal maximum, our best prior example of rapid warming. You've learned that the PETM damaged coral reefs and insects, among other effects, and is likely that our future is headed down a similar path or worse. In this lesson, you'll explore what might be causing the recent and rapid temperature increase. Maybe we can find a way to slow it down, stop it, or reverse it. A good place to start is with the factors you learned about in our blue planet that control Earth's temperature. What factors affect temperature? Can you remember what might cause a planet to warm up? In our blue planet, you examined factors that allowed Earth to support liquid water on its surface. Select all factors below that contribute to Earth's ability to support liquid water. I like that they have Alfredo in here. That's funny. So go ahead and scan through those and select your best guess here. Is it the amount of magma in the mantle? The distance from the sun, distance from Venus, distance from the moon, distance to Mars, the atmosphere, or the albedo? Okay, and you should select those three. And here we go. How do we predict Earth's temperatures under varying conditions? In this lesson, use the same temperature model used in our blue planet to see what happens to Earth's temperature as you change different factors. Even though the model is limited, it can still be used to test non-greenhouse gas factors. As you learned in our blue planet, there is one key factor that this calculation does not take into account. What major factor is missing? Okay, and the answer here is going to be atmospheric composition. They did not have that as part of that calculation. So we're going to test out some of these factors. Albedo, distance, and the atmosphere all contribute to Earth's ability to support liquid water. Which of these factors are involved in the recent rapid change in Earth's temperature, though? Is Earth's temperature being affected by a completely different factor? One factor we have yet to look at is the amount of energy that comes from the sun, or its luminosity. Could changes in the sun's luminosity be what is heating up Earth? Select a factor below to investigate, and let's just go in order. Okay, if we look at the albedo, what albedo values are possible for planets? Albedo is the fraction of incoming light that is reflected by a celestial object. And that's a new vocab term, so I'm going to go ahead and write that down in my notes. An albedo of 0 means no light is reflected. An albedo of 1 means all light is reflected. The table lists the albedo data for all planets in the solar system. What are the maximum and minimum albedo values of these planets? So as I scan through here, Mercury, Venus is pretty high, 0.65. Oh, but beaten out by Saturn. And that's pretty cool because if you think about which of these planets can you see in the night sky, have you ever been able to see Venus or Saturn? These are two of the brightest planets. You can also see Jupiter out there too, usually. And then Mercury, Mars appears a little bit red. Those are fainter. You can still see them. The one that's the hardest to see, though, is Mercury. Okay, whoops, I said Saturn, I entered Venus. But anyway, so there's Saturn, and then Mercury. Okay, what about Earth's albedo? It's going to change. Earth's current albedo is 0.31. Using Earth's current albedo value, the table below shows the temperature of the Earth if all other factors are kept at their default values, and Earth had no atmosphere. Identify the effective temperature in the data below. Then convert the temperature to Celsius. To convert from Kelvin to Celsius, subtract 273. Okay, so let's see, let's find the effective temperature, and then we'll subtract 273 from that. going to get a value of negative 19.1. And that's pretty cold. And remember, that's if there is no atmosphere. Okay. Planetary parking lot. What if we could change the albedo of Earth? The substance with the lowest albedo on Earth is fresh asphalt, used to pave streets and parking lots with an albedo value of around 0.04. What would the temperature of Earth be if the entire planet were covered with fresh asphalt? We have calculated the effective temperature of Earth if its albedo were 0.04 in the table below. Identify the effective temperature and then again convert to Celsius. So we're subtracting 273. Okay, so the effective temperature given that would be 275.7. If I subtract 273, I am at 2.7. Okay, so we paved Earth and it would absorb enough heat to support liquid water without an atmosphere. Pretty neat. While we calculate the temperature of an asphalt-covered Earth, is this realistic? No. Okay, yeah, you can't pave the oceans. Oh, I wonder if they're going to talk about... Okay, I see where they're going. Here we go. There are actually... Okay, they're not going here, but this is a little side note. There's this reservoir in LA, and they put these shade balls on top. So imagine going to McDonald's and playing in the play place, which of course you can't do right now, but it's like those. And they put them all over the reservoir. Can you think of why that would be useful? So it's not just to increase the albedo, although that was probably helpful and maybe could be used on a massive scale. Although you would block algal growth here, which is what they were trying to do, and reduce evaporation. Yeah, so maybe I'll link this for you guys too, so you can read into that further if you want. Anyway, back to our lesson. All right, so now let's go to the other extreme of fresh snow, which is 0.85. What would the temperature of Earth be if the entire planet was covered in fresh snow? So we're doing the same thing here. We're taking this number and subtracting 273. So it's a little hard to do that, but if you go down, we got 273, right? So go down one and then down another. We're at negative 73.3. So I explained that wrong. So minus 73, get rid of that 73, go down 100, go down another 100. There we go. Cool to try to do that without a calculator. All right. While we can calculate the temperature of a snow-covered Earth, do you think this is realistic? You will be scored on. Okay, so what do you think? Yes, it snows in most places already and is a really cold winter, can make a snowball Earth. No, Earth has always been too hot below the polar regions to support widespread snow and ice. No, the ice would melt in summer. Yes, shifts in Earth's climate could bring about a snow-covered Earth. What do you think? Okay, and so maybe you guys have heard of the snowball Earth, but this idea that when the climate shifts, it can produce a situation on Earth where it is completely covered in snow. So let's investigate how those have happened in the past. In 1991, the eruption of Mount Pinatubo in the Philippine Islands set a huge cloud of dust, debris, and gas into the atmosphere. One of the gases produced, sulfur dioxide, reacts with water and sunlight. In Earth's upper atmosphere, this reaction forms an aerosol, a fine mist of droplets of sulfuric acid. So think aerosols are what you'd spray out of a can. That's an aerosol can. Make like a paint, like spray paint. Make a hypothesis. What will the eruption of Mount Pinatubo and the aerosol it releases do to Earth's albedo and temperature? Would the aerosol decrease the albedo, decreasing Earth's temperature? And remember, I just jotted down a note in my notebook, but a decreased albedo would actually increase the temperature, right? Think of the asphalt Earth. The aerosol increased albedo, decreasing Earth's temperature. So would it reflect more and then reflect more sunlight back to the atmosphere and then decrease Earth's temperature? And that's going to be my guess. Let's test it out. So can natural processes change the albedo of Earth? Albedo? Okay, so here we go. On Mount Pinatubo, it changed Earth's albedo, raising it by 0.007 to an average value of 0.317. We have calculated the effective temperature in the table if the Earth was at 0.317 below. And then we'll have to convert. So Earth's temperature is predicted in this model at negative 18.2 degrees with a normal albedo of 0.31. How much colder is the Earth in the model after the eruption? Okay, so first, two parts here. Subtracting out 273. The difference there is about 20 minus 0.2, so that's 19.8. At a negative. And so how many degrees colder is that? What's the difference here between 19.8 and 18.2? 1.6. Okay, so that's a huge difference from one volcano erupting, 1.6 degrees. Luckily, other factors like the ocean prevent such a drastic change from happening so quickly. Oh, and then we have to, was our hypothesis supported? Aerosol increased albedo, decreasing Earth's temperature. That is true. Okay. Making a note in my notebook that a volcano can act like snow, which would increase the albedo and decrease the temperature. Okay, and this is... Okay, I think this is interesting, so little side note. So imagine all of that is creating almost a barrier between the light coming in and then being reflected. Okay, one more slight diversion. That made me think that was in 1991. So I was wondering what other volcanic eruptions have happened. And here we go with a volcanic explosivity index. In Chile, 2011 was the last big one. And then, I don't know, just scrolling through here. Big props if you can pronounce that. All right, back to our lesson. So is Earth's albedo changing? Snow and ice are the most reflective substances on the surface of Earth. What trend did you notice about the snow and ice in then and now? Levels of snow and ice are generally not changing. Levels of snow and ice are generally increasing. Levels of snow and ice are generally decreasing. I'm going to guess that because of the glaciers. What is the most likely direct cause of the snow and ice loss you observed? Increasing temperature. Melts ice, that's what happens. All right, and our last question here. What would happen if Earth's albedo from the loss of snow and ice? Earth's albedo will remain the same. It will decrease or it will increase. Remember, an increased albedo from snow decreases the temperature. So if we decrease the albedo, that would happen if there's less snow. Less light being reflected, and the lower albedo means more light is absorbed. If all else is constant, what should change in Earth's albedo mean for the global average temperature? The global average temperature will increase. Okay, so if we have a lower albedo, that usually increases your temperature. There we go. Well done. All right, so a warming Earth causes ice and snow to melt. Melting ice and snow causes Earth's albedo to fall, which causes Earth to warm even more as less solar energy is reflected into space. This type of cycle is called the positive feedback loop. In a positive feedback loop, one of the factors, in this case warming temperature, affects the other factor, snow and ice or albedo, causing the first factor to increase even more. In this case, any change to the system is magnified many times by the positive feedback, just like when a microphone has feedback in an event or a concert. Can you think of other positive feedback loops? For example, let's just take it outside the realm of biology and into psychology for a minute to get an idea of this, but let's say you're angry, that means, or your dad's angry, that means that it's really tense around the dinner table, that means everybody else is really tense, and that increases and it keeps increasing the factor of the environment at your dinner table being really terrible. In another way, in a more positive, so it doesn't have to be a positive thing for it to be positive feedback is what I'm trying to get at. But if you want to do positive, like if you started laughing and then someone else starts laughing and then everybody's laughing. Okay, but then into like other examples of positive feedback within biology might be childbirth. So when there's a hormone that gets released, which causes contractions, which increase the hormone released all the way until the baby's born. Okay, so let's figure out how a positive feedback loop would affect this albedo. Here we go. Could albedo be responsible for the observed temperature increase? Okay, so I just want to show you what my notes look like right now. Right here, I like to make these little arrows to shorthand these effects that happen. So if I already have a warming Earth, that's going to increase the ice melt, decrease the albedo, increase the temperature. And that is the positive feedback loop. So maybe I draw a circle or a loop from temperature back to Earth. One factor is going to increase the other one. Okay, here we go. So let's read through our options. Here we have no, Earth's albedo is decreasing because snow and ice are melting, but it is the temperature increase causing the melting, not the other way around. Okay, or is it no, the Earth's albedo can't change? Yes, Earth's albedo is decreasing due to loss of snow and ice. This decrease in albedo will result in more energy being absorbed and temperature increasing. That sounds the best to me. Or yes, Earth's albedo is in a low point in its natural cycle. The decrease in albedo means more energy is absorbed by Earth, making it hotter. Or no, Earth's albedo is decreasing due to paving and asphalt projects worldwide. Oh, okay, read that wrong. So go ahead and select no, Earth's albedo is decreasing because snow and ice are melting, but is the temperature increase causing the melt, not the other way around. Yeah, so it is part of that feedback loop, but where does it all start? So here the Earth's albedo is causing the temperature increase, not necessarily. The temperature is increasing, which is decreasing the albedo, increasing the temperature because of the decrease in the melt. Does that make sense? I hope so. And then I don't know, this is kind of funny, these just two pictures, Mercury and Saturn. Well, remember, lowest albedo, highest albedo. All right, so let's select another factor. Let's go with the distance. All right, here we are talking about the perihelion and the aphelion. All right, so Earth's orbit around the sun is an ellipse, like a slightly flattened circle. Because of this, Earth's distance from the sun varies slightly. At its closest point to the sun, called the perihelion, Earth is 0.98 AU or astronomical units away. At its furthest point, called an aphelion, Earth is 1.02 AU away. And remember, it is defined by the distance between the sun and the Earth. So we have calculated what temperature Earth would be at each distance, assuming all other factors are constant. Identify the effective temperature and then convert to degrees Celsius. Okay, so let's take a look here. We have 256.4 minus 273. Go ahead and do that math. Okay, so we got negative 16.6 and negative 19.4. So which one is cooler? The aphelion, and that's the furthest from the sun. That makes sense, by about 3 degrees. So that's kind of a big difference. Oh, it is likely that these changes in distance are responsible for the observed rapid temperature increase on Earth. No, the Earth is spiraling away from the sun every day and it should be getting colder. Yes, the Earth is spiraling closer to the sun every day and that's what's making it hotter. Yes, the sun is getting closer to Earth, making it warmer. No, changes in distance would result in an increase and a decrease every year. Yeah, because we have a cycle, it's an orbit, but no overall trend. And here it just reiterates that point. As Earth orbits the sun, its distance from the sun changes. This change in distance leads to slight changes in Earth's temperature. However, various factors minimize this change in temperature. Additionally, these changes are routine in that they occur each year. It does not explain the rapid increase in the Earth's temperature that we've noticed occurring over the past century. All right, so let's now test the atmosphere. All right, so here we've seen this graph before. This is a breakdown of the gases that make up the atmosphere. Let's make a hypothesis. What do you think are the top contributors to the greenhouse effect that allows water to host liquid water, as you saw in Blue Planet? Okay, so you're making a hypothesis. So go ahead and just make a guess based on these different factors, and we'll see what we figure out here. Gas trends. What gases follow the same trend as temperature? Shown at the right is a graph of the observed temperature increase. Below are individual graphs of gas concentration over time. All right, so, whoa, we got data overload here. Let us slow down and figure out which one of these are going to follow this general increase in temperature. So, yeah, basically nitrogen, did that change? No. Oxygen, did that change? No. Argon, did that change? No. Specific humidity over land and ocean, humidity being a measure of water vapor. So what do we see? From 1970 to 2010, in the ocean and the land, we see a general increase that potentially matches the temperature. So let's go ahead and select humidity. Carbon dioxide, we have an increase as well. Nitrous oxide increases, and so does methane, but neon and helium do not. Okay, and I am going to add these observations. So add that. And maybe here I want to be more specific. Oh yeah, actually. Let's look from, where does it start to increase? Very good to look at the axes from 1922 present. I'm saying here with an uptick in 1930. And let's see, same here with methane. All right, so now I got those added to my graph. I can go on to the next. Conclusion, is the atmosphere behind the warming trend? Given the evidence you've investigated, could the atmosphere or parts of it be behind the observed warming trend? And I would say yes, several atmospheric gases follow the observed warming trend, including some known greenhouse gases. And we say those greenhouse gases like carbon dioxide and methane. I'm going to go ahead and take notes on that. Okay, and let's check our last one, luminosity. Variable solar luminosity. How does solar energy output change over time? One of the factors that affects Earth's temperature is the energy output of the sun. This data is called its luminosity. Shown are data of the sun's energy output since humans have been able to measure it via satellite. Here we have total solar irradiance during solar cycles. So what do you notice is happening? Cycle 21, down, cycle 22, up, down, cycle 23, up, down, cycle 24, up, down. And then they're looking at this 6-month mean successive solar minimum. So here we have between 1986 and 1998, and then all the way to 2010, we have these successive solar minimums. What are the maximum and minimum values for solar luminosity shown in the data? Maximum luminosity, total, so that's going to be over here on the left. What is the maximum? I would say something like 1364. The minimum luminosity, somewhere down here, 1359. Okay, so I guess they're telling us that is actually pretty small. I'm going to go ahead and enter in this into my chart. So each cycle is how many years? Go ahead and calculate that. We have from 1986 to let's say 96, looks like 10-year cycles. I'm going to put in some numbers here. 1360 watts per meter squared. That's the measure of luminosity. And then I'm going to say to about 1363. Or what pattern do you see in the data? It looks like it's a cycle again. Luminosity is rising and falling. How many years does it take to get from peak luminosity to peak luminosity? So that looked like about 10 years to me. Oh, and they're estimating it, 11 to 12 years. Average luminosity. What temperature should result from average luminosity? The average solar luminosity values from the data was around 1362, or 1 LS, which is another measurement for luminosity of the sun. we have determined the effective temperature of Earth if all other factors are held at their default value in the table below. Of 18.2. Oops. Okay, remember the negative 18.2, so that's on the average. And now let's look at the minimum. So take this number. Okay, and then enter in 18.7, it's the calculation, and that is a little bit lower with the minimum, that makes sense. Less light coming in from the sun. Okay, and the final thing here, what is it saying? Maximum solar luminosity value identified was 1364. We converted it by dividing. Okay, so they found 1.002, and we want to know if we look at the table to determine the temperature of Earth with 1.002 luminosity of the sun, if all other factors are held constant. Okay, so let's take this value now. Subtract 273. You should get negative 18. And so if we're tracking all these numbers, this is just a little bit, it's not really even that much warmer, right? Just a tiny bit warmer than the average. Okay? So, is luminosity behind the warming trend? We varied from negative 18.7 to negative 18, and the average being 18.2. So does that appear to affect temperatures at all? No, luminosity changes go up and down. Temperature trend is generally upwards. I would say that's probably, and also that the luminosity predicts smaller changes. Okay, so here we have varying answers here. No, the luminosity changes go up and down, we can see that. But the temperature change here is generally upward. And here, yes, the changes are appropriate in time and in range. Those do seem to add up, but it's still too small a change to be due to that. Okay, so we've checked all four. And now we need to identify the culprit for factors, but which is the most likely responsible for the temperature increase? Which of the factors you investigated, albedo, distance from the sun, solar luminosity, or the atmosphere, does the evidence indicate is most likely the cause? And I would say the biggest effect there is probably the atmosphere. Amount matters. Are all gases present in equal amounts in the atmosphere? You have seen atmospheric gas concentrations measured in parts per million. This stands for parts per million, or ppm, yeah. At a concentration of 1 ppm of carbon dioxide for every million particles in the atmosphere, only 1 particle is carbon dioxide. Some other concentrations are in parts per billion or even parts per trillion. Which of these concentrations is the largest? So if you have 1 in just a million versus 1 in a billion versus 1 in a trillion, that's the largest concentration. Shown in the table to the right are concentrations of greenhouse gases you have identified earlier. Order them in the list below from the most concentrated to the least concentrated. Okay, so here we go. They're all in parts per million. And we are ordering these. So which one is the most concentrated? That looks like carbon dioxide at 397. And then we have methane at 1.79, and then nitrous oxide. And then water vapor is not included in the dry atmosphere. And we're going to use this concentration. Okay, this is helpful. 50,000 parts per million for water. So that puts water at the most. Okay, a lot of water. What is the strongest greenhouse gas then? Looking at volumes of these gases, which is probably the greatest contributor to the ability of Earth's atmosphere to retain heat? So if we look at, here we have the volume in both parts per million and inches percentage. So this one has the highest amount, so probably water would be the great, it has the most amount of particles, so those are the ones that are going to be heated up by the sun's rays and bounce around in that, contributing to retaining the heat. So that is, water is one of the most potent greenhouse gases for that reason. Identity matters. Do all greenhouse gases behave the same way? Water is the most abundant greenhouse gas. However, there are other factors to consider. Shown at right are data on the lifetime of the greenhouse gases you have been investigating. Lifetime refers to how long a sample of that gas can remain in Earth's atmosphere before escaping, reacting, and being bound to another substance, or precipitating as rain or part of rain. Although water is the most abundant greenhouse gas, what does its lifetime mean for its contribution to the observed warming trend? So water vapor has a really short lifetime. It's up in the air and then it's back down on the ground. So it is probably less than other gases because it's not in the atmosphere very long. Correct. Water is often called self-regulating. What it means is that we put too much water into the atmosphere from anthropogenic processes, it will naturally fall out in the atmosphere as rain or snow within 3 days. It's really difficult for humans to affect the amount of water in the atmosphere. All right, so if it's not water, then which is it? Which one of these has the next longest lifetime in the atmosphere? Or has the longest and the highest concentration? That would be carbon dioxide. So let's put it all together. The Earth is warming. The trend is most closely follows the Earth's atmosphere. Within the Earth's atmosphere, the components that is most likely responsible is carbon dioxide. Okay, so where might it be coming from? It's the culprit, but where is it coming from? Earth's natural greenhouse effect allows it to support liquid water. Thus, all life, including humans, are supported as well. However, in the past 100 years, the average global temperature has risen rapidly. This is a phenomenon which trends with and is strongly tied to the observation of carbon dioxide in the atmosphere, which has also risen recently. Where has all the carbon dioxide come from, though? And that is what we will explore next week in our next lesson. But come to the live lesson tomorrow and we'll practice a lot of those concepts, as well as talk about, I'm specifically going to go into an example that is relevant to us in the desert and how snow or sand in the desert can have an effect on the snowmelt and increase the albedo in the mountains, or decrease, I suppose. Yes, decreased albedo increases temperature, like asphalt. Okay, that is this lesson, Finding the Cause, and I will see you guys tomorrow.